Looks like we can start. Welcome back, folks. So for today's class, we're going to be finishing off section 8.3 relative to the assignment 8.3. And this is going to be the last assignment for the entire semester. So we're nearly there. We're going to look into a little bit in section 8.8, start that section, see what's going on in the world of vectors. But I feel like we won't be able to really get this section completed, even if we spent all day on it on Monday. It's a pretty big section. There's a lot of fun topics here. So the assignment that did involve these exercises, I've turned them into suggested exercises. We'll still start this section, take a look at what's going on with it, but we'll be considering next week just a full-on final exam review week, which seems to make sense if the exam is 2 hours, then 2 class periods is just 100 minutes to try to get that review in. So I think that'll be a great way to optimize our time. I'm going to essentially turn section 8.8 into an extra credit section for the final exam. There'll be one question on the final exam from that section, and it'll be worth some extra credit points on that final exam. It'll be just the last question. So if you decide to go beyond what we'll end on with the content here, I'll finish off these notes and solve the work completely so you can come take a look into it. And these would be the suggested exercises that will help you rack up that extra credit if you're looking into that. But that's our plan so far to finish out the week. When we come back next week on week 15, we'll just be fully reviewing for the final exam on both days, Monday and Wednesday. Any questions at the moment, folks, with those announcements, or any questions to start us out? Okay, well, let's jump back into polar coordinates. Then when we come back on next Monday, we'll just reviewing the whole course. So just a reminder, this will be the last official assignment, and there'll be possibly 1 or 2 questions on the final exam, nothing too major, on getting through polar coordinates. If you're doing well on assignment 8.3, you're going to be fully prepared for those questions on the final exam. So here's where we left off. We were converting between the Cartesian coordinate system into the polar coordinate system. The prior problem was going in the opposite direction. And for converting to rectangular form into polar form, these are the 2 equations that we used. So we took the point -1, 3, plotted it here. And the equations start off kind of nice first. To get the value r, the distance from this point here where the red dot is, to the pole here where the red dot now is, really we're just using Pythagorean's theorem in a certain sense. We took x squared plus y squared equals r squared. The last step is kind of the tricky step. R is a directed distance, which means it can be positive, negative, or 0. And so the final equation, tangent theta equals y over x, this is a step that gets pretty confusing because we're now solving the trigonometric equation, tangent theta equals -3, and it can only give you values from here to here. The -3 means the output's going to be negative as well. And we got -1.25 radians. In fact, that's a valid value to use for theta. So we made our official answer -1.25 radians. So this is a rotation we're looking at. But we use the negative root 10, to say go the opposite direction, the diametrically opposed direction here, and you end up on that point there. Second method was just add pi to this angle, takes it to 1.89 radians, and then just use the positive root 10 to get that r value. So that's the rundown on what we did right before closing out class. I think we ended just a couple minutes early last time. Any questions on this refresher problem here? Okay, and just a reminder, sorry, go ahead.
Sorry, can you just go over again how you got the radians?
Yeah, are you talking the very first one right here, the negative
Yeah,
1.2?
yes.
Absolutely. So we start with the equation here. Tangent theta is y divided by x. So the y value is 3, the x value is -1. Then I imported that equation over here, just substitute in the information. And now when we get to tangent theta is -3, this is where we have to now do some calculator work. So let's pull this up. I gave an answer in radians, and I'm going to leave that up to you. You can give me something in radians or in degree measurement. That'll just be up to your stylistic way of reporting the answer. Let me check what mode I'm in here. Looks like I'm in radians on this one. So when I go to put this in the calculator, it's going to be arc tangent -3, which gave us the negative 1.25 upon rounding radians. So the solution to that equation there, negative 1 point, tangent theta is -3, gave us negative 1.25 radians. But that's kind of a strange value to work with. It turns out as a hack, you can use the negative root 10 and just get the right point because you're moving backwards across this, landing in the right spot where our original point actually was over here. But if we were going for positive root 10, then this terminal position, negative 1.25 radians, doesn't look right. We terminated in quadrant 2 way up here. The way we work around that is we just take plus pi. Recall that the period of tangent is pi itself. So if you take negative 1.25 radians, add pi to this, let's compute that out. Negative 1.25, add pi. It comes out at 1.89 radians. And we can double check in our calculator. If we to take, say, tangent at 1.89 radians, keep in mind it is rounded, so we're not getting exactly -3, but that's pretty close actually. That tells us we have the right value. It's just an approximate value, 1.89 radians. So the actual theta up here was 1.89 radians. Unfortunately, tangent inverse gives you exactly one answer. It can only give you this one in the wrong quadrant. But at pi, that's the period of tangent, you're just still going to get -3. Now you're ending in the correct quadrant, matching with what we see way up here. And that's why we have a 1.89 radians and a positive root 10 for the R value to direct the distance. What's kind of cool is either approach works. You could have used negative 1.25 and a negative root 10. But I think the more standard answer is to use the positive root 10, in which case you have to use 1.89 radians. But does that make sense on getting that radian measurement?
Yes.
Awesome. It's kind of a tricky question again, because this is suddenly a bona fide trigonometric equation, which is looping back into inverse functions that have particular domains and ranges we have to be critical of. Looping back into, we had to be mindful of what the original diagram was to maintain the right angle, and using periodicity of tangent to get 1.89 radians. So it's a pretty busy problem out of nowhere. So conversions going from rectangular to polar are often kind of messy like this. But going backwards, this is kind of the fun approach. If you have it in polar, getting into rectangular is automatic because the coordinates, both x and y, are completely solved for. You just crank it out like this way. Plug in the r value, plug in the theta value, and you just get a number. No equation to solve, really. Well, other questions or comments, folks, about the warm-up problem? Okay, well, let's finish off the notes then. There's just a few more examples to take a look into. Here's another kind of a fun thing to do with polar coordinates. Really, it's sort of a review problem because we're going to plot the polar points, the major skill behind this section. But once you have points in the plane or in the polar coordinate system, a big question you'd want to resolve is, what is the distance between those points? And you can think in these terms. You could just take these points, convert them back into rectangular coordinates, then use the distance formula for the Cartesian coordinate system, and that's a pretty valid approach. But let's do it the polar coordinate way, just to see how it will work if we decide to just stay in polar coordinates. Which makes sense. The first thing we're going to do is plot these points. If we're going to find the distance between them, we need a good visual on how to do this computation. So on the first point, 2 and 11 pi over 6, let's start by just putting down a quick polar axis. Next thing we focus on is the rotation. 11 pi over 6 is almost a complete rotation, 2 pi. We're just off by 30 degrees from one full rotation. So to that, my eye, that looks like almost 30 degrees away from a full rotation. So here's 11 pi over 6. We go a distance of 2 on this new ray that we formed. So here's 1, 2. So that point right there plotted is 2, 11 pi over 6. Then let's do it again. 5 pi over 4 is first pi over 4 goes this way, 45 degrees. 3 pi over 4 goes this way, 135 degrees. So 5 pi over 4 is the one going this way, 225 degrees. So on the 5 pi over 4 ray that we just formed, we go a distance of 3, trying to keep that unit length the same as we go. So here's the distance 1, 2, 3. Then right at that spot, here's coordinates 3, 5 pi over 4. We want to find the distance between these points. So if we can find the distance of this line segment in green, let me try again, between this line segment, our work will be done. So that's the setup so far. All I've done is plotted the 2 points and put down a line segment representing that distance. Well, once we have all that on paper, if we can get that angle theta right there, this turns into a law of cosines kind of problem, just out of nowhere, which is kind of a fun review problem as well. The diagram is already kind of busy with 3 different rays we're looking into and coordinates and so on. So we can abstract away from this right here and turn it into just a triangle problem from section 8.2. Trying to make those segments proportional. Okay, so we want to find that distance d. The polar coordinates gave us the lengths. The distance from here to here is 2, so we can label a 2 here. Distance going this way and this way is 3, so we can label a 3 going this way. All we're missing is that internal angle. If we can get the angle here, law of cosines is going to give us the exact distance. Will give us the square distance, and then we'll just take the square root. So now it boils down to, what is this measurement right here? We could call it, say, theta. Let's put it on the original diagram as well. And here's one way to think about it. When we rotate it to this ray, 11 pi over 6, here's what the rotation looks like. We have theta is 11 pi over 6. But if we are only going from here to here, that means we have to subtract off another rotation. That'd be the 5 pi over 4. So we'll go subtract. This rotation, here to here, is 5 pi over 4. But that's an excess rotation we didn't need. Theta is just going to be this tiny band. So it's as if we rotate the whole 11 pi over 6 part, but then to get the angle theta, we subtract the 5 pi over 4 part that theta has nothing to do with. It's the internal angle there. So subtract 5 pi over 4 next. And that's going to give us our angle theta. Let's work this out in Scratch for the fraction work. I didn't think far enough ahead for the space of doing the Scratch work there. Our least common denominator is going to be a 12, so let's multiply that by 2 over 2. That's 22 pi twelfths. Multiply this by 3 over 3, so minus 15 pi twelfths. And we get theta is 7 pi over 12. We could convert it to degrees like we did when we used law of cosines, but we can keep it in radians as well. Might as well. There's no real reason to do a conversion there. But did that make sense to folks using this trick right here, the subtraction of those angles to get that internal angle? Okay, well, now that we have a 7 pi over 12, let's label it here. And this is specifically the situation that law of cosines works really, really well on. If you call that angle theta or 7 pi over 12, the idea with law of cosines is that the square of the distance squared, we can find that length as long as we know these two opposite legs, side lengths here and here, and the internal angle between them, which we do, 7 pi over 12. So we can say distance squared is going to be this side length squared plus the opposite side length squared, so 2 squared, minus 2 times those same legs again, 3 times 2, times cosine 7 pi over 12. And you know what's a really kind of cool thing about this sort of problem is, even if you got this subtraction backwards, it doesn't matter. You're going to get the right answer because cosine at 7 pi over 12 is equal to cosine at negative 7 pi over 12. That's because cosine is an even function. It essentially deletes that internal negative sign. So even if I just by mistake went 5 pi over 4 minus 11 pi over 6, and I got a negative angle, it doesn't matter. If you put a negative or positive angle here in the calculator, you get the same exact value. So we're just about have the square of the distance. We just need to import all this into the calculator. So here's the law of cosines review problem that we've done this week. Back into the calculator, here's what we're going to get. 3 squared plus 2 squared minus 2 times 3 times 2 times cosine 7 pi over 12 gives us the 16.10. And just to observe that comment on the negative sign, notice if you do put a negative there, same exact value. The calculation doesn't update. So we have 16.1058. Our distance here is going to be a positive length. We don't want a directed distance like we were doing with r. We want the honest distance. It's either 0 or some positive quantity. So when we take the square root of both sides, we're just going to take the positive root. Distance is root 16.1058. So finally, we've got a distance. Once we abuse the calculator a little bit further, it's square root 16.1058. And we're rounding to 1 decimal place. That would round out to a 4.0. So the distance between those two polar coordinate points is not exactly 4. Putting in the 0.0 is just a reminder that we did round it. It's close to that after rounding. Well, we did, folks. If we were to convert these both into rectangular coordinates, the process would work the same. But that formula is kind of messy. It might look sort of similar as well, however. You're eventually going to take a square root. But here we're at least reviewing multiple topics at once. I think this is the cleaner approach as well, getting through this problem. Well, any questions at all? Getting the distance between 2 points in polar coordinates? Okay, our last topic is looking a little bit into equations in the Cartesian coordinate system and the polar coordinate system. And these last two examples are kind of used as a justification for why we care about the polar coordinate system to some degree. The thought is some equations are just better naturally expressed in polar coordinates, or maybe better naturally expressed in rectangular coordinates, depending on the curve that we're trying to give. So here's those two sets of equations from before. Recall the first two equations are great from going from polar to rectangular. And the last two are great for going backwards, rectangular form, the Cartesian coordinate system with x and y, back into polar form. So we'll convert this equation, x squared plus y squared minus 6x equals 0, into polar form. Maybe just as a quick bit of side work on this. Let's visualize what we're getting into before we even put it into polar form. For dealing with equations now in polar coordinates, it's good to see what the graph of those equations would look like in the first place. And a cool trick in this calculator is you can go to graph settings and you can use a grid like this one, but if you click on this, it becomes a polar axis grid, the same kind of polar axis grid that we were using in all of our last problems. There's 11 pi over 6. Over here, not plotted, is the 5 pi over 4 and so on. So we put in this equation, x squared plus y squared minus 6x equals 0. Here's the equation that pops out. Looks like a circle. Center is somewhere over here. It's not completely clear that that's what it was in this form, unless you start completing the square and rearranging things on that equation. But that's what we're expecting to see, some equation of a circle. If we put this in polar form, we should see that equation a little bit more clearer. And here's what the work would look like. The first bit is we can take this x squared plus y squared that we see and just rewrite it as an r squared. So that's a kind of a nice immediate transition or substitution. This becomes r squared minus 6 times x. But the x here, we could rewrite as r cosine theta minus 6 times r cosine theta equals 0. So those are our two substitutions. They're pretty quick. It's now in polar form. And this is where the instructions start to get a little bit vague. Now that it's in the equation in polar form, we want to simplify it as much as possible. I'm not going to be too critical when I grade these. If it was an exam question and you got to here, I would consider that full credit. But it's important to know that this is not the simplest form of this equation. Equations in polar coordinates have lots of interesting things going on with it. One thing we can do with this equation is just factor out r. If we factor out r, we are left with r times r minus 6 cosine theta equals 0. Now we can use the zero product property. We have two things multiplying resulting in 0. So that would mean r is 0, or r minus 6 cosine theta is 0. So now we started with one equation. In our attempt to simplify it, we now have two equations, and that's not necessarily considered simplified when you've doubled your equations, even if one is a simple equation. On this one right here, we can do something kind of nice, however. We can write this as r equals 6 cosine theta. And this is the typical way we would usually like to write this equation. We think of r as being the dependent variable, theta as being the independent variable. We get different directed lengths, distances r, for different input variables theta. Much like, say, in this equation over here, or say this one where the red dot is, y would have been the dependent variable, the one that's solved for, and theta is the independent variable. So this one's a nice equation. Thinking of theta as the independent variable and r is the dependent variable. But now we have to reconcile this equation here says the original x squared plus y squared minus 6x equals 0 can either be described by the simple equation r is 0 or a totally different equation, r equals 6 cosine theta. It turns out there's some redundancy on this one. If you say allow theta to vary, take on any radian measurement, when it takes on pi over 2, cosine pi over 2 is 0, and you get r equals 0. That means r equals 0 is redundant. Let's say, put this in words. This is redundant since at pi over 2, r equals 6 cosine theta becomes r equals 0. If this was impossible to ever be a 0, maybe it's 1 plus 6r cosine theta, then we would have had to keep that equation because that's extra information not captured in this one. So now that we know r equals 0 is a redundant equation, we can say our end answer is r equals 6 cosine theta. Put a box there to express that's our actual equation. So this was the equation of a circle. It looked like it had center 3, radius 2. And this is the equation of a circle, possibly, if we did the math right on the conversion. It looks like a simpler way to actually write out that circle versus this one. This is a bigger amalgamation of different variables. Let's put it in the calculator to see if it comes out right. But first, any questions at all getting down to that line? Okay, well, to double check if this is going to come out right, let's first hide that equation, put in r equals 6 cosine. You have to type in theta in that way. I'll put in a theta. But notice that's really the same circle. It goes from a r value of 0, that was way over here, all the way to a r value of 6 when cosine takes on a value, say, 0 or pi. You're way out here. You get a r value of 6, not 0 pi, but 0 or 2 pi. And that's the same exact circle as we saw here on the red dot. Let's kind of overlap them just for emphasis. So that's kind of a neat and cool way to just express a circle. So kind of up to you if you put this in standard form, which was showed the center and the radius, that equation would have been even more complicated. To me, this is just a much cleaner way to represent a circle now. We'll also practice going backwards next. That's kind of neat to see how these actually plot out in a coordinate system like the polar coordinates. Next one we're going to look into is r equals 1 plus cosine theta. We want to convert this one into Cartesian form. Let's actually take both sets of these equations down or work with them on the next page, just for the sake of easy reference. Okay, so going backwards, we're starting with the polar coordinates, r equals 1 plus cosine theta. We want Cartesian form, which means there should be no r's, no thetas left over, just x's and y's. First, let's take a look at what this equation even is to get a feel for what we're getting into. R equals 1 plus cosine theta. It's kind of a simple equation, not too different than r equals 6 times cosine theta. When it was r equals 6 cosine theta, we got a circle. If it's just r equals, say, 6, we get another circle. That's because every point here on this line has distance 6 away from the pole. And if theta can be any value, you just get a circle centered at 0. So now if you go 1, here's a circle with radius 1. But what happens when you put plus cosine theta? Plus cosine theta, we get this kind of a weird shape. Looks kind of like a heart that's rotated. That, if you're thinking about the Cartesian coordinate system, looks like a pretty complicated curve in all honesty. It has a cusp right here, a really sharp point. And it curves gently. Out here, it looks a bit like a circle, just a little wobbly. But then the curvature gets more extreme, and then it hits the cusp again. This is a pretty weird and bizarre curve. And the more interesting and bizarre these curves get, the harder they're going to look like in Cartesian form. These Cartesian coordinates starts to become pretty complicated trying to get descriptions of these curves. One reason it's so complicated is, notice this is going to fail the vertical line test just immediately when you look at it. That means there could be lots of functions that go to actually describe something that looks like this. So writing it as an equation that gives us lots of implicit functions, let's first just copy down what we have to start. R equals 1 plus cosine theta. It's easy to get kind of stuck on this sort of stuff. To get x's and y into the problem, we have to eliminate r has to be gone entirely. We have to eliminate cosine theta as well. So let's see here. What's one thought? If you can get r squared into the problem, that eliminates it because you could swap that for x squared plus y squared. And if you could get an r cosine theta into the problem, this whole thing will turn into x. So one thought is just multiply both sides by r. We'll have r squared on the left equals r plus r cosine theta on the right. We can make a swap right here. Another substitution right here. And here's the new equation. X squared plus y squared equals r plus just x. So we're getting through it. That's progress. But notice the problem we still have with this thing. There's still a value r hanging out that we have to figure out something to do with. So we have to eliminate that r to get it fully in Cartesian coordinates. Here's where the algebra sort of gets uncomfortable. Really, the only clean way to get an r out of there is not using either one of these equations. Sure, you could solve this equation for r. It's y divided by sine theta. But then you have theta in the problem, so that's not giving us good progress. Really, the only equation we can work with is this one. So here's the next thought. If r squared is x squared plus y squared, we hate to have to take this step, but if you need just r power 1, like we have here, take the square root of both sides. Here's why we hate this step. This becomes r equals positive or negative square root x squared plus y squared. But now the trouble is r can absolutely be negative. We've seen plenty of examples on these notes when that happens. So I can't just by default throw away 1. I might be losing information. So putting this all together, our equation now looks like this. X squared plus y squared equals, in place of r, positive or negative square root x squared plus y squared plus x. But this is, again, kind of a problem. Same sort of problem we had on the last equation, where we had r equals 0, r equals 6 cosine theta. If it's two equations, it's not necessarily as simplified as possible if we can find a way to reduce this. Plus and minus right here is now giving us two equations. So here's where we're going to take this to the letter, simplify this as much as possible. But this is a new topic at the very end of the course, essentially. So if you did this and left it in this form as a homework problem, I'd say that's perfectly fine. I might make a comment that you can simplify further. If you got to this step on a final exam situation, then you really did the major concept of the problem, doing those conversions, and you'd get full credit on a final exam. But if we really had the time and mental energy to simplify as much as possible, here's the next thing we can do. Let's isolate the part that's ambiguous, the plus or minus root, the thing that's giving us two equations. So subtract this x from both sides. X squared plus y squared minus x is now plus or minus square root x squared plus y squared. Now we can raise both sides to power 2. It makes the left-hand side a little bit more complex. We won't FOIL it out. We'll just leave it in this factored form, power 2. But power 2 helps the right-hand side. It eliminates the ambiguity. It's now just positive on the right-hand side. It also eliminates the square root, so that's a nice side benefit. We have the equation x squared plus y squared minus x squared, so it's a complicated one, equals x squared plus y squared. So this innocent looking equation, r equals 1 plus cosine theta, well specified in polar coordinates. If you have to convert it into rectangular coordinates, it becomes a giant mess. That's a complicated curve we were looking at. And so the equations in x, y is complicated as well. But hey, at least we did it. That's the steps we'd have to take to get to rectangular coordinates. Well, any questions at all, folks? Getting down to that end result? Okay, well, for the last bit of time we had, I thought it would be kind of interesting to just look into a little bit more with this curve right here. This curve is pretty complicated. In X and Y's, this is what it would look like. And so that means you can really imagine what would happen if you made it worse. Suppose you squared this. Now it's got this pretty weird looking peanut shape. Again, if we had to convert this back to XY coordinates, probably even worse down here than before. But in polar coordinates, that's a really simple specification for something that's ordinarily really complicated to describe. So this is one of the reasons the polar coordinate systems shine so well. Some curves are just naturally described this way. If we add even more, say sine theta, that looks like some weird shape as well. Maybe raise it to an arbitrary power. Power 3 looks like a upside down heart. Start going really crazy with these powers, like power 12. Now it looks like maybe a hat or something, who knows? Raise this one to power 31, and it's something different still. These are just random changes here. And this is, again, other than the high powers, a pretty simple equation to write. But if you had to describe this curve in XY, this could be pages and pages of pages of the description of that one curve. And there could be ambiguities that we don't see clear ways to get rid of. This could be just a monstrous nightmare to describe in the Cartesian coordinate system. But if this is something that you had to machine in the real world, maybe you're dealing with an experimental reactor, and that curve comes up, that's where polar coordinates are really, really helpful. Well, we've completed this section, folks. 8.3, like we mentioned, this is the last official section of the semester. Any questions at all before we change over to just a quick peek into section 8.8? Okay, let's close this out. Oh, sorry, go ahead, Luke.
Yeah, sorry. I was just curious what r equals 1 plus cosine theta looks like on the graph in Cartesian form, if that's okay.
Oh, gotcha. So what would it look like in the graph on Cartesian form? So what I think you mean by that is it's not so much the grid that's going to make the difference. So if I go r equals 1 plus cosine theta, then this is still the polar coordinates that we're looking into when we see that polar curve. But if you want to plot this as, say, a different sort of axis, let me know if this is thinking along the right thoughts. If you want to think of this as, say, a horizontal, so that this is now a theta axis, and that's a horizontal variable rather, and r is the vertical variable. So going this way, this is now the r axis. Then in a real sense, we're visualizing r equals 1 plus cosine theta in Cartesian coordinates. It's not x, y, but we're thinking of a horizontal coordinate theta, vertical coordinate r, and this is what it would look like. R equals 1 plus cosine. And when I put down x, think theta. And this is what that curve is going to look like. Really, it's just cosine theta moved up by 1, and the r value is the output. Does that make sense? Does that align with the question you were asking?
Yeah, I think so. I was just mainly curious what all the XY that we had derived at the end of that example was in Desmos. I was just curious about that.
Gotcha. Yeah, let me take a look into that one. So let me put back here a theta. And going back to this one, let's go back to this just because it feels like the right kind of setting. Plotting this one is kind of interesting. We put in x squared plus y squared minus x power 2 equals x squared plus y squared, then we get that same kind of shape. It's plotting this in a totally different kind of way. The technology is actually working pretty hard to make that plot work. But either way we look at it, we're getting the same exact shape as before. Does that make sense with that question there?
Yes, it does. Thank you.
Absolutely. Yeah, sorry for misreading your question on that one. But this is kind of an interesting opportunity to just mess with this one as well. Say you put a power 3 on it, then the equation in black is the new Cartesian equation. It changes in a lot of ways. Put power 31, changes quite a bit. It was power 2, matching the original. If you do weird things like add e to the x, these things just get more and more convoluted and complicated as you go. It's kind of interesting to see what the changes might be as you add more random stuff like e to the power theta. On this one, seems to have caused some kind of crazy explosion where the rendering is just not working out quite right anymore. It's actually slowing down Desmos. Not sure we could get any resolution on that. So that one looks like a pretty bizarre looking equation. Other questions at the moment? Okay, well, let's save this up. And for the last amount of time, doesn't look like we have a great deal of time to make some serious segue to section 8.8. And just as a reminder, section 8.8, this is really just going to be extra credit for the course. The homework assignment has been demoted into suggested exercises, and the extra credit will be the last question on the final exam, will just be a topic from some of these problems right here that you might see. One problem with a few parts, all for extra credit. To see what you're getting into in section 8.8, let's first maybe do example 1, and I'll come back here and finish out the notes, finish them completely. So if you do want to use this as a resource to go for the extra credit problems, this will be filled out. But let's at least end class just looking into example 1, why you might care about vectors. Kind of interesting thing about this section is it's going to feel a lot like polar coordinates when you look into how example 2 goes, how example 3 goes. This is really just law of cosines coming back again. So it feels like a rehash of the same information we've done. What's new is just the point of view. We'll say a scalar is any quantity from the set of real numbers indicated by R, or even the set of complex numbers indicated by that symbol C. And a vector is a quantity that can represent vaguely two different things, magnitude and direction. We'll say big vectors are equal if and only if the magnitude is the same and the direction is the same. So a quick example of a vector could be something, say, like this. Of a vector that starts right at the origin, we'll call those position vectors later on in the notes. You can indicate the vector by putting in, say, a directed arrow. So there's an initial point to the vector, a terminal point. Let's say this goes 1, 2, 3, 4, 5, and then 1, 2. The way we might write this vector is bracket 5, 2. Well, that's just visualizing the actual vector. When we say a vector has to have a magnitude and a direction, here's what we mean by both of those in this context. The magnitude of, I should give this a name, let's call it V for vector. The magnitude of that vector, V, is this, square root of 5 squared plus 2 squared. But that's just using the Pythagorean's theorem again in the distance formula to find the distance from here to here. Because this is 0, 0, it's really 5 minus 0 plus 2 minus 0. So 5 squared plus 2 squared. So it's just root 29. That feels like polar coordinates. If you're finding, say, the r theta value, the magnitude is r. Only difference for vectors is we think of our magnitudes as only ever being positive. In polar coordinates, it could be negative. The direction of V is Well, we know the magnitude, that's just literally the length of the arrow. The arrow didn't have to start at 0, 0, it can be anywhere and still considered the same vector. But the direction is this measurement, theta. We could use tangent inverse to solve for theta, just like we did on the warm-up problem we looked into at the start of today, and we would get the direction of theta as well. Change theta, and you're going to change the direction this points into, but keep this as, say, just a rigid length, never change it, and it'll have the same exact magnitude. So that's what a vector could look like out in the wild. It's a weird one because it has no context. So if you're thinking of vectors as things with actual physical context, it's good to compare against scalar values and vector values. So recall, scalar is just a number in the set of real numbers are. And a great context for this is maybe, say, driving. If you're driving anywhere tonight or recently, the speed in, say, miles per hour of 30 is a scalar value. So your speedometer is only giving out a scalar value to represent your motion. But there's a lot more going on in the physical world. If you want to think of driving your car as a vector, you have to combine two things, both magnitude and direction. The magnitude would be, say, the speed. Magnitude is 30 miles per hour in this car we're imagining to drive. And we also need a direction. We can say some angle theta and be vague like before, but maybe you're on some road, maybe it's a country road, or you just happen to know you're going due north. That allows us to say direction north for this example on just, say, driving a car. I should say what this is about on the notes, just for clarity. Different example could be, say, wind speed. The wind speed would have the actual speed, the direction of the wind. But a scalar value would be, say, something like temperature, just one numerical readout with no other information that has a direction to it. So these are the objects of study in section 8.8. If you decide to go through for the extra credit problem, probably the best way to do it is definitely read the section, practice the suggested exercises, come back to section 8.8 as a reference. I'm going to fill out all the notes here. And it's not going to be a major computation. It'll just be something quick with vectors like these, doing some operations, doing a dot product, that kind of stuff. But sorry for the lack of time to get too far into this section. We got through the major results, the things you really need trigonometry for your next math classes. Polar coordinates is one we need to spend a good amount of time in. Well, any last questions at all, folks, before we call it a day? Okay, when we come back next week, then we'll just be reviewing for the final exam. We'll take 2 days since, again, we can make more progress in section 8.8, but that would probably just put us somewhere in the middle of these notes. This is a kind of an abnormally longer section. But have a great weekend, folks. We'll be back to it now, reviewing the final exam next week. Thanks. Have a good one.